Previous two videos we looked at how the sine and the cosine graphs were generated by following the unit circle around and getting those values by following the x-axis and the y-axis and making the sine and cosine graphs. Now let's look at the sine and cosine graphs to see how those form waves and how we analyze them. All right, now, this is one trip around the circle following the y-axis. So this is following the y-axis over time. And this is following the x-axis over time. And this time right here is a special time that we call a period. Okay, so right here we call the period for the wave. Now the period of the wave is the time that it takes to make one complete trip around the unit circle counterclockwise. So this makes one trip around the circle, and this makes one trip around the circle. That's one period. That could happen in 1 second. It could happen in half a second, 5 seconds, whatever the time. The time is however long it took. The period is for one specific trip around. Now, if you keep on going around the circle, that generates more, and that right there would be 2 periods, and however much time it took to do that is just regular t. We make a uppercase T for period, lowercase t for regular, just time. Now, this we call the amplitude. That's the maximum amplitude, which is the highest point of the wave. This is the lowest point for the wave that is also an amplitude. And the amplitude, you just take the absolute value of it. That's 1, and that's 1. That's -1, that's 1. The absolute value would just be 1. The highest part of the wave is called the crest. The lowest depth is called the trough. And the distance from here to here we call wavelength. And that's denoted by the symbol lambda. I'll draw that symbol over here as well. That's wavelength. The crest is here for the cosine, and the trough is here for the sine. For the amplitudes, this is cosine. All right. Now, as you continue around the circle, you could generate more of those, and that would be 2 periods for cosine. That's 2 periods for sine. And they're not to scale. They could be drawn actually equal to each other, so I should have kind of drawn this out, but that's okay. Let's see. Frequency. There are 2 types of frequency. We have angular frequency and frequency. Frequency is defined as the number of waves per second. And that's how many waves you have in a specific amount of time. And let's do an example of that graphically. Let's say that the period, the typical period for a general wave is 1 second, and we draw that. And now let's say that we're going to increase the frequency, and in a time of 1 second, we're going to have more than one wave. So this is regular time. Okay, this is time, but it's also the period. Now, this is time, though, but not the period. Let's double it and say that we have 2 waves in a time of 1 second. This is capital T, and that's lowercase t. So the period is now 0.5 seconds, but the time is 1 second. But this is the time for a frequency of 2 waves. So 2 waves per 1 second. This means that we increase the frequency. If we increase the frequency, we decrease the wavelength. Okay? If we increase the frequency, we decrease the wavelength. Now let's do that one more time to show you what that means. That's a time, a regular time of 1 second. Let's now divide this up into thirds. That's 1 wavelength, so 1 period. 1 wavelength, but 2 periods. 1 wavelength, but 3 periods. And we've increased the frequency, and you can see now that we decreased the wavelength. So the lambda went down as the period went up. This means that there's an inverse relationship between frequency and period. When your frequency goes up, your period goes down. That inverse relationship is given by f is equal to 1 over t, or t is equal to 1 over f. And the unit for period is the second, but the unit for the frequency is called a hertz, H-E-R-T-Z. And hertz is the number of oscillations over time, the number of waves over time, beats per second or whatever. Now, angular frequency is very different. That is equal to 2 pi f, and that's basically how often you repeat the full circle value given the number of waves per second that you have. So this is dependent upon 2 pi intervals. If that's an interval of 2 pi, and that's another interval of 2 pi, you have 1, 2. So that's a frequency of 1 wave per second times 2 pi for the number of intervals. And that would be 2 pi over t, because f is 1 over t, substitute frequency for 1 over t. So the angular frequency is how often the wave repeats in a given angle measure or radian, and frequency is how many waves you have per second. So this is angular or radian dependent, so it's the frequency multiplied by 2 pi. And let's spend more time going over the 2 pi. That has to do with the circumference of the circle. So let's draw the circle one more time. And the circumference of the circle is the distance all the way around. And that's 2 pi times the radius. Now, the radius for the unit circle is equal to 1. And so you end up with 2 pi. So that's omega times frequency. That's 2 pi times that. That's where we get the 2 pi from omega. Now, that's the distance. Velocity is equal to distance over time, and that time could be the period for the wave, but the distance is 2 pi. And so now we get the velocity is 2 pi over t. Well, that's the same thing as the angular frequency that we had over there. It's 2 pi over t. Now, if we look at the distance around in radians, and the distance around in degrees, we see something else. The distance around in radians is 2 pi r. The distance around in degrees is 360 degrees. Now, let me write this out. This is 2 pi r, and I'm going to put radians. And that's 360 degrees. A radian is the measurement of distance along the arc of the unit circle, and that's about 1 radian right there. We're going to prove that in just a second. If we divide both sides by 2 pi, you end up with r equals 360 over 2 pi. That's going to be 180 over pi, and that's degrees. So 1 radian is 180 over pi degrees, and that's about 57.3? 57.3. Alright, so 1 radian is 57.3 degrees. That means that about 57 degrees, this arc length here that we call S, is 1. Okay? That's 1 radian. There are 2 pi radians in the unit circle, and that's 6.28. So there should be 6 of these plus 0.28, and roughly, if we draw them out, 1, 2, 3, 4, 5, 6, and that's 0.28, and 4 should be a little further down, 5 should be a little over. But you get the general idea. The arc lengths are 1 radian across each, and that's the S. That's where we get S equals R theta. And r is s over theta, the equation that we discussed earlier in the year with circular motion. We get that from analyzing this. Looking at the degrees side, we looked at the radian side, so 1 radian is 57.3 degrees. Now let's do this the opposite way and divide by 360, so we get 1 degree on this side. You end up with pi over 180 is equal to 1 degree. And let's... That's 0.017 arc length. So 0.017 would be very, very small. That's 1 degree. Right there. 1 degree is 0.017 radians. Okay, that's it.